So in the previous video, we have discussed the definition of topologies. Now we will continue. We will discuss in this video some definitions and some examples. So now in brief, we tell about definitions. Topology. For topology, we have to see three conditions. First is, in short, we are going in short because in previous video we have discussed broadly. Now we will do in short. T is a topology. Means T is a topology. If topology of X any set, if Y belongs to T, X belongs to T. First, second, A belongs to T, B belongs to T, A intersection B belongs to T. Third, A alpha belongs to T, then union of I belongs to A alpha belongs to T. Delta is equal to index set. Index set. So these three conditions satisfy any subfamily of set of X, then it is a topology. Means I belongs to T, X belongs to T, A belongs to T, B belongs to T, then their intersection belongs to T, or A alpha belongs to T, and A1 A2 belongs to T, their union is also belongs to T. Three conditions are satisfied, then it is a topology, otherwise it is not a topology. We have discussed this one. So now we will take some example also. We have also seen, suppose this is X equal to A, B, C. This is a set. So what are the topologies? Suppose T1 is equal to phi X A, T2 phi X B, T3 phi X C. Phi, this is a topology because first condition satisfied, phi belongs to T, X belongs to T, phi belongs to T, X belongs to T. Any intersection means phi, suppose you take phi and X belongs to T, their intersection, phi intersection X is phi belongs to T, or you take this one also, A belongs to T, or if you take any two sets or all sets, then union is also belongs to T. So these are the topologies, and these topologies are comparable or not comparable. We see what is comparable. These are the topologies, first thing. And comparable or not comparable. Comparable means either T1 subset of T2 or T2 subset of T1. Not comparable means not comparable. T1 not subset of T2 or T2 not subset of T3, T4, any. So these first, these are not comparable because here A, B and C. Means T1 is not subset of T2, T2 is not subset of T1. So these are, means here T1 is not subset of T2, T2 is not subset of T3, T3 is not subset of T1. Subset means all elements, here all elements of T1 are in T2. But here A, this set is A, here is not A, here is not this set A. So these are, all these are not comparable. These are the topologies but not comparable topologies. Now we take some more examples. Now suppose X is equal to 1, 2, 3, 4, 5. X is equal to this one. And if suppose here it is given T, phi, X, 1, 2, 3, 2, 3, 4, 1, 5. So we want to see, check whether it is a topology or not. T is a topology or not. So first condition is x belongs to T, phi belongs to T. Phi belongs to T, x belongs to T. First condition is satisfied. Okay. Now we come second. A belongs to T, B belongs to T, A intersection B belongs to T. Suppose we take A. A is equal to 1, 2, 3. And B is equal to 2, 3, 4. A belongs to T, A belongs to T, B belongs to T, A belongs to T, B belongs to T. Now we see A intersection B, A intersection B. A intersection B means common element, which is common in both A and B. So what is common? 2, 3. 2, 3. So we will see 2, 3 is whether exists in T or not. 2, 3 is in T or not. Here 5x. 5x is this one. 2, 1, 2, 3, 2, 3, 4, 1, 5. So 2, 3 is not belongs to T. 2, 3 is not belongs to T. So this is not a topology. This is not a topology. Okay. And so we will see 5x, maybe 5x belongs to T, but intersection, or suppose intersection is T, maybe union is not belongs to T. A alpha, union A alpha not belongs to T. We'll take example for suppose here we see x is equal to, this is A, B, C. Now we find topologies. Find topologies. T1 subset of T2 subset of T3. Like this one. Find three topologies where T1 subset of T2 subset of T3. Like this one. So we can make T1 phi x, phi x, T2 phi x A, T3 you can make phi x A B A. So these are three topologies where T1 subset of T2 subset means all elements of T1 are in T2, all elements of T2 are in T3. So in these three topologies are such that T1 subset of T2 subset of T3. Now comes some more definitions. Now suppose let x is a definite set. Let x is an infinite set. X is an infinite set, then any topology, then any topology containing, consists or containing phi x and any phi x and any subset of x. If x is an infinite set, here we have discussed some examples of finite set. Suppose x is infinite set and T is containing phi x and any subset of x, then then T is called, or T is known, T is called confinite topology, or confinite topology, or we can say T1 topology, or we can say finite complement topology. If X is infinite set, then any subfamily or topology which consists phi x and any subset of x is known as confinite topology, T1 topology, or finite Now topology is given like this one: A infinity, A infinity, where x belongs to R and x greater than A. X belongs to our real number and x is greater than A is known as right hand topology. This is known as right hand topology. Suppose here, like this one, minus infinity A, x belongs to R, x less than A. This is known as left hand topology. Left hand topology. This is known as left hand topology. In topology, x is equal to suppose phi x and 1 or 0, phi x 0. X is 0 1. Then t is any topology. X is set 0 1 and t is a topology phi x 0. This is a topology is known Sierpinski topology. Sierpinski, S-E-R, Sierpinski. So this is if x is 0 1 and topology is consists 0 phi x and set 0. So this is known as Sierpinski topologies. Okay. Now we have discussed in last video T closed set and T open sets. T open set and T closed sets. If Xt is topological space, Xt is a topological space. Xt is a topological space. Then we have seen, we have discussed or we have read all elements of T. All the elements of T are known as T open sets. All elements of T are known as T open sets. Then any A belongs to T. All A belongs to T are known as T open sets. All elements of T are known as T open sets and other than are T closed and x minus A are known as T closed set. A belongs to T are known as all elements of T are known as open sets and other than all subsets which are not in T are known as closed set. T closed set. Maybe some here subsets may be both closed and open. This may be possible. And topological space. Topological space Xt is known as dual space. Dual space. If any topological space is known as dual space if all the subset of X, all the subsets of X are either T closed, either T closed or T open sets. So a topological space is known as dual space if all subsets of X are either T closed or T open. Means all subsets will cover. It will cover all subsets of X. Or maybe some sets, some all subsets may be open, both open and closed also. It is also possible. Suppose we take here some examples. X is suppose A, B, C. X is suppose A, B, C. Now we take T. T is equal to phi X A B C. Phi X A B C. So what are T open sets? Here T open sets. T open sets. All elements of T are on T open sets. Means all these phi X A B C are T open sets. So what is T closed sets? What will be T closed sets? T closed sets. T closed sets means X minus A. X minus means X minus phi. X minus phi is X or complement. Complement of phi is X. X minus X, phi. X minus A, X is this one. Minus A means BC. X minus BC, X is this one, ABC, and minus BC means A. So here we can see all sets phi X A B C, phi X A B C are both T open or T closed sets. Here you can remove one thing, so you can make T open and T closed different, like this one. Suppose you take here or the same set X is equal to same set ABC and T is equal to phi X A. Suppose this is, what is T open sets? T open sets. These are T open sets, phi X A. These are T open sets. T closed sets. Complement this one X phi. What is this one? BC. BC. So this is T open sets or this is T closed sets. But this is dual space or not. You will see what is the definition of dual space. All subsets of X are either T closed or T open. So this is X A B C. What are the subsets? Phi X A B C A B B C C A and ABC. ABC is this one. These are the whole subsets, total subsets. So here we see phi X A, phi X A, phi X, phi X B C are T open or T, but this is not here anywhere, and maybe T open or T closed. At least either here or here it should be exist. All subsets are either T closed or T open. So this is not dual space. This is not dual space. This is A space. Suppose we take ABC. Now we take other example ABC. Then suppose T, this one phi x a ABC a AB and BC, or we can say BC, not BC, ABC, AB, and suppose here this is AB. Now, or we can say here CA, 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 or AC, AC. So here we have taken phi x a, and this is here. Now, or we can say B also, BBC, or all ABC. Then what are T open sets? T open sets are T open sets. Phi x a, AB, CA, B, BC. These are T open sets. Now T closed sets. T closed sets complement x, phi, BC, C, here B, AC, A. These are T closed sets, means complement x minus A. So now we check all these, all subsets of x are phi x, A, B, C, A, B, B, C, C. So here we check all subsets are coming here or not. Phi x is this one. A, B, C, A, B, B, C, C. Or these are common. A, B, B, C, C are coming. So all subsets of x are either T open or T closed. So this space, this here, topology is given. This is dual space. If this topology is given, then this is a dual space. Dual space means all subsets of x, either T open or T closed sets. So here, these are some examples of topologies. So in topologies, we have to remember definition of topology, or whatever topic is given. First, definition must be understood very clear. What is the definition? Phi belongs to T, x belongs to T, phi belongs to T, x belongs to T, A belongs to T, B belongs to T, A intersection B belongs to T. So A belongs to T, B belongs to T, their intersection A belongs to T. Their intersection A belongs to T. Their intersection phi belongs to T. Their intersection B belongs to T. So this is a topology. A belongs to T, B belongs to T, A intersection B belongs to T. And whatever sets we take from here, their union is also belongs to T. So these are the basic some definitions we have to remember. Comparable, not comparable. Comparable means T1 subset of T2 or T2 subset of T1 is comparable. Not comparable means T1 not subset of T2, neither T1 not subset of T2 or nor T2 subset of T. Okay. So this is comparable, not comparable, or strictly comparable means suppose T1 subset of T2 and T1 is not equal to T2. T1 subset of T2 or T2 is not, T1 is not equal to T2, then T2 is called strictly final topology. Then T1. Strictly final. T2 is bigger. So if T1 does not equal to T2 means strictly final, or this is strictly weaker. Like this. So these are some basic definitions. So in next video we will discuss some theorems and some more, we will take more examples of theorems and open sets